Hello everyone. We're going to discuss about notches and wears. So notches and wears are also Hello everyone. We're going to discuss about notches and wears. So notches and wears are also used for measuring discharges, but they're mostly used for open channels rather than pipes. So a notch, as you know, nowadays it's a very common thing in mobiles. So here is a notch, here is a notch. So notches have different shapes and sizes. But in our case, the notch will be something like this, where you'll have water here, and over the notch, water will flow out of this. And if you look at it, the rate of flow will depend on how much water is above the sill level of the notch. This is called the sill. We can also call it the crest. Now, discharge over this kind of a notch is given by velocity into area, but the velocity is not a constant value in this case, because as you can see, when water flows over this notch, velocity at this point and velocity at this point will be different, because different amounts of heads are acting on both these points. So at this point, the velocity will be smaller, and at this point, the velocity will be larger, and velocity being given by the formula V equals root over 2gh, where h is the height or the head available to cause the velocity. Now let us look at the discharge over a rectangular notch. So we are looking at the notch from the front, so water will come out of this based on the head. And now we know that the velocity at different points will be different, at different depths will be different. At this point, the velocity will be smaller. At the lowest point, the velocity will be the highest. And therefore, we cannot simply use an average velocity. So let's try to find out a proper expression for the discharge. For that, we're going to divide this whole cross-sectional area through which flow is taking place. We're going to divide it into elementary strips. So let us consider one elementary strip, a horizontal strip, because along a horizontal line, the velocity is going to be same as we have considered. It's a function of h only. So at this point, at this point, at this point, the velocity will be same. And therefore, we can, instead of taking an elementary area like this, we are taking a complete strip, a horizontal strip, as an elementary area. Now, the area of this elementary strip will be given by dA equal to B, which is the width of the notch, and multiplied by dH, where dH is the thickness of the strip. And the strip will be located at a depth small h, where capital H is the total head available and small h is the head available over the elementary strip. So that is the area of the strip. And velocity through this elementary strip will be given by V equal to root over 2g small h, because that is the head. And therefore, the discharge will be this velocity multiplied by the area. Now, the total discharge can be obtained by integrating this thing. However, the limits of integration will be from h equal to 0 to h equal to capital H. So therefore, we are going to write the limits as 0 to capital H. And once we plot the values of these things, the area is given as B into dH, and the velocity is given as root over 2gh. And B and root over 2g can be taken out of the integration sign, and under integration remains root over h, that is h to the power 1 by 2, and dh. So after integration, we arrive at this result. And finally, the expression becomes 2 by 3 multiplied by b root over 2g and multiplied by capital H raised to the power of 3 by 2. So that is the discharge over a rectangular notch, given that the head of water available is capital H. Now again, this is actually the theoretical discharge. The actual discharge will again be given as Q actual equal to some coefficient CD multiplied by the theoretical discharge. And therefore, the expression becomes 2 by 3 CD multiplied by B root over 2G and H to the power 3 by 2. So that's how we find out the expression for discharge over a rectangular notch. Sometimes notches are made triangular. So let's discuss a triangular notch then. So a triangular notch is like this. The principle is same. Based on the head, available head, the discharge will increase. But again, the velocity at different heights will be different. So therefore, we are going to find a proper expression for the total discharge. Now let's look at this triangular notch from the front. The triangular notch will have a certain angle. So this angle of the notch is called theta, suppose. It can be 60 degree, it can be 90 degree, or any other angle. Now, if this is theta, then again, just like the rectangular notch, we are imagining an elementary strip, again horizontal strip. And this horizontal strip will have a thickness dH, and the head above that horizontal strip is small h. And the total head available from the bottom of the notch is capital H. Now again, we have to find out the area of this elementary strip to find out the discharge. Now in this case, the area is not simply B into dH, where B is the width. Here B is actually variable. So let's call it small b. And this small b is a function of this height or head. As head becomes 0 at this point, the width is maximum, and at the bottom, when the head is maximum, the width is 0. So let's try to write an expression for that. So this is our elementary strip. We're going to find out this width b. We know the thickness is dh. So let's look at the geometry of this whole triangle. From top to bottom, the total head is h, and head above the elementary strip is small h. So the remaining portion is capital H minus small h. And we are interested in finding out this width. So we're going to divide this into two halves, and this angle, half of the angle, will be theta by 2. And so we are taking this half of this triangle here. Now this dimension is b by 2. This head, this height is capital H minus small h, and therefore we can write as b by 2 equal to h minus small h tan theta by 2. So therefore, the total width is twice of capital H minus small h tan theta by 2. And therefore, we can write as the area, this elementary area is dA equal to twice of b by 2 into dh, and b by 2, as we know, is this expression, twice of h minus h tan theta by 2. And therefore, the discharge through this elementary strip, dq, let's say, is equal to the velocity multiplied by this elementary area dA, and velocity is root over 2gh, and the area is given as this much. And therefore, the total discharge over the notch Q can be obtained by integrating this expression, and the limits are again from 0 to capital H. And if that is the case, then we can take these items out of the integration sign, and whatever remains inside integration will be these terms. And finally, we are going to arrive at an expression for the total discharge, that is Q equal to eight by 15 root over 2g tan theta by 2 and h to the power 5 by 2. So that is the final expression for discharge. Again, this is only the theoretical discharge, and the actual discharge will be given by Q actual equals 8 by 15 multiplied by some coefficient of discharge CD, and rest of the expression remains the same. Now let's look at a real notch. So a notch will look something like this. So this is a triangular notch that you can actually buy. So in this notch, you see there are two scales. These scales may not always be marked properly in a commercially available notch, but what we get here is, on one side we have height or head, and on the other side we have liters per minute, that is discharge. Now what does it mean? If you have the height or head measured above this point, in that case, you can calculate the discharge above over this notch. But so that you don't have to do all these calculations, some manufacturers will simply put the discharge values because they already have the formula. So based on the height available, they will just put the value of discharges. So you don't have to calculate again and again. Similar kind of notch may be available in rectangular shape as well. So that is how discharge through these notches can be obtained. Sometimes instead of this, the value of CD as manufactured has obtained. So they will do some experiments and compare the actual discharge to the theoretical discharge and find out the value of CD, and they will print it on the product itself. So you don't have to again find out the value of coefficient of discharge. You just apply the formula and multiply that with the coefficient of discharge to find the actual discharge. Now let's discuss about weirs. So a weir is similar to notch, but the only difference is that they are bigger than notches, and instead of small appliances, they are provided in the rivers and streams. So they look like this. This is a rectangular weir, and this is a triangular weir. Then they are generally made of concrete or masonry. Now they will be coming in different shapes and sizes. So the shapes will be, this is a rectangular weir and also broad crested. This is a triangular weir. This is a trapezoidal weir. Sometimes they will be sharp crested like this. As you can see, the edge or the top is very sharp. Sometimes they will be broad crested, and sometimes they will be ogee crested, which is the downstream side or surface of the weir will be matching the flowing liquid or flowing water. So these are some different types of weirs. Now let's discuss about the difference between triangular and rectangular notch. So a triangular notch is mostly useful for measurement of very small amount of discharges. As you can see, if we look at here, in this case and in this case, let's say the discharge amount is same. But the problem is, for a rectangular notch to have the same discharge, the head is very small. And this very small amount of head is difficult to measure. But to have the same discharge, here in the triangular notch, there is a considerable amount of head, which is easy to measure. And in this case, since the depth is very small, the effects of surface tension and viscosity may be affecting the discharge formula, and your coefficient of discharge will be varying very rapidly. So you can no longer consider that as a constant value, and therefore that CD value that the manufacturer has provided you will be applicable only beyond a certain value of discharge. For very small values of discharges, that will not be very accurate. But that problem can be solved in case of triangular notch, because for a small value of discharge, you will have a considerable head, and therefore the effects of those surface tension and all those things will be negligible. As you can see, in this large river, we have provided a rectangular notch, but in this very small stream, we have provided a triangular notch. Sometimes two-stage weirs or notches are also used. That is, if the range of discharge to be measured is very wide, that is, sometimes the value of discharge will be very small, sometimes they will be very large. So in that case, we may provide this kind of two-stage weirs or notches. That is, for small discharges, since here the width of the notch or weir is small, so it will require a larger head. Similar is the case for this kind of a weir. And when the discharge increases, just to make sure that the water level behind the weir doesn't increase too much so that the river flow is affected, so we make the width bigger. And similarly in this case. So these notches and weirs are flow measuring devices. They're used in different situations, sometimes to measure this discharge over in rivers, sometimes in this kind of streams, sometimes when you have leakage through some kind of embankment, earthen embankment, suppose, sometimes when there is pumping, but you cannot find out the discharge rate of a pump. So in that case, you provide some kind of tank like this. And so you collect the water, and in the tank, you provide some kind of notch. So in that notch, instead of measuring the discharge again and again, you simply note down the water level above the notch. So based on that water level, it is very easy to note down the water level every minute or every half a minute. And that way you can find out the discharge with time. Otherwise, it will be very difficult to measure those kind of discharges, because every time in front of this kind of a pump, you'll have to put a large tank, then measure the time to fill up this tank. And if the value of discharge is variable, then it is even more difficult, because then you have to replace that tank and put up some other tank, and it is really difficult. So this kind of application of a notch or weir is helpful in those cases. We'll continue our discussion later in some other lecture. So for this one, this is enough. Thank you.